Okay, so today we'll be covering equivalent systems of forces. Now, the basic idea here is that oftentimes the actual system that we're talking about is a bit too complex to start doing math on, but we can simplify things by kind of combining forces together, moving forces around in order to help ease our calculations. So obviously, previously we've been talking about the equilibrium when it comes to particles. So infinitely small objects that still have some sort of mass or what have you. You can still have forces that add up and come to some sort of equilibrium. So so the net forces acting on that object are zero. Most of the time, however, we can't necessarily simplify our design into particles for your force analysis. Anything that we're actually making takes up volume, it's got size, shape, mass, so on and so forth. So we need to consider the size and the shape of the body in question and where the forces that we're applying to it act upon their body and how that affects the equilibrium. So we often talk about rigid bodies. So basically, this is us saying that any deformations that occur to the body due to the loads applied are small enough that they can be treated as negligible. So basically, we're assuming the object in question is infinitely stiff. Again, the degree to which that's a reasonable assumption depends upon the object and the loads in question. So I've got my calculator here. If I'm applying a load to it, you can actually notice it is bending a little bit. It's flexing a little bit, but it's not flexing enough that the change in the geometry of the object is going to have a significant effect upon the forces that are being applied to it. It's not going to change the equilibrium of the object. Whereas if we have, say, something like this wrist pad here, well, it can't even hold its own weight. So, if I try to do a model saying that this is a rigid body and apply a tiny little bit of force downward here, then that becomes a not valid assumption anymore. The deformations are large enough that the original assumptions that went into doing the calculations for the equilibrium they don't work. But essentially you need your object to be stiff enough in order to resist the forces that are being applied without moving too much. So we'll be talking today about rigid bodies. We'll be talking about rigid bodies for most of the course. So we'll be talking about how loads get applied to rigid bodies, and basically how we can take various forces or loads that are applied to those bodies and replace them with simpler equivalent systems. So basically, one thing that when we start talking about rigid bodies instead of particles, the forces don't change their definition when applied to rigid bodies. So if they're acting at a in a particular direction, then they've still got that magnitude and direction. But where the force is applied upon the body will have an effect upon how that body reacts to the forces applied. So we'll be talking about moments very shortly, but I'd like to introduce the concept of internal and external forces first. So external forces is something that is exerted on by other bodies on the rigid body. So we're talking stuff like these fellas here pulling on this rope, trying to pull this truck. You've got friction from the wheels. You've got a normal force here that is coming from the roadway. It's pushing upwards. in order to basically prevent that truck from falling through the road. And we also got gravity going downwards here. So all those have an effect upon the body as a whole. All those forces would show up on the free body diagram of the truck. Got internal forces too. So internal forces are basically what hold the forces that hold an object together. So basically you can think of them as forces that are being transmitted through a body. So basically, if I got my cup here and I push down upon it, when I push down upon it, the force that I apply here is going to increase the amount of force that this cup transmits to my lower hand here. Right now, the weight being applied to my hand is just the weight of gravity. When I press downwards, I got the weight of gravity plus that force that's being transmitted through. So on the free body diagram, there would just be, right now there would be two forces applied. Gravity and the normal force from my hand. Add an external force, we add a third force, and that would just increase the magnitude of the reaction force from my hand. But inside, essentially, we've also got these internal forces that basically transmit all of those external forces to the points where they're being applied to other bodies. So for our initial static analysis, we don't consider internal forces on the free body diagram. We do have external forces on there. We'll be getting into calculating and representing internal forces on a free body diagram later in the course. So one thing to keep in mind is that we have this thing called the principle of transmissibility. So essentially, if you take a force and move it along its line of action, it doesn't affect the conditions of equilibrium for a rigid body. So for example, I've got a water bottle here. If I'm holding this water bottle here, I'm exerting a force upwards that is equal to its weight. If I support the water bottle from the bottom, again, I am exerting a force that is equal to its weight. And both of those will be acting through in the same line of action. So both of those forces are equal, and they're acting in the same direction along the same line of action. So that means that those are equivalent forces. The state of equilibrium for the water bottle right here and the state of equilibrium for the water bottle right here is exactly the same. So going back to the truck, if you pull the truck with a rope from the front, or if instead you get those guys who are pulling on the rope and have them push from behind, as long as the line of action is the same, as long as the total amount of force is the same, then those are equivalent. This is exactly the same equilibrium condition as this one is. So basically shifting that force along its line of action does not affect any of the other forces acting upon the truck. So that'll be, and I'd like to emphasize that is something that works for external forces. That having been said, it wouldn't necessarily be the same case if we're trying to look for internal forces. So for example, we've got this situation here. We're pulling on this object here from either side. From an external perspective, that's exactly the same thing as if we had both those forces located at A. But internally, essentially, because those two forces would be canceling out at the same point, or pulling together at the same point, internally, this wouldn't develop any tension. But from an external perspective, for equilibrium purposes, these are the same things. And of course, the same thing works out if you're pushing together. If you're pushing together from the ends, or kind of pushing together at the sides, as long as the total forces being applied are the same, as long as they're along the same line of action, then that is equivalent from an equilibrium perspective. So what happens essentially if if perhaps we shift some forces so that they're not acting this, so that they're not acting in the same line of action. So I'm sure you guys will remember from one of your math courses last semester the concept of a cross product. This is necessary to understand basically how a force acts about a point. So we need to basically be able to calculate the vector product or the cross product of two vectors. Now I'm going to use the term cross product in this course just because it is the most popular term to use for this concept. Your textbook, at least the Beer and Johnson one, uses the term vector product, but they're equivalent terms. They're synonyms. But if you go to Wikipedia and try to look this up, the article is called cross product, not vector product. So you want to. I'm using that term just because it's more common. If you have to look up some help and how to calculate them, cross product's usually the way to go. But the cross product of two vectors is basically defined as a separate vector that has a line of action that's perpendicular to the plane that contains those two vectors. So again, we've got a plane here. Those two vectors are on that plane. Its magnitude is proportional to the size of each of those vectors and the sine of the angle between those. So if you're changing the angle of the vectors that you're taking the cross product of, if the angle is 0, then the cross product is 0. If the angle is 90, then the cross product is at its maximum. And then it has a directionality. The directionality is based upon the right-hand rule. So basically, the directionality here is if you curl your fingers from the first vector towards the second vector, the cross product will be oriented in line with your thumb. So essentially, P cross Q, your fingers curl around there, gives you V. Another way you could look at it, some people don't like to do the curl thing. Some people like to kind of orient their hand in a particular direction, their fingers, their index finger in a particular direction. They like to curl, point out the middle finger, and then have the cross product would be directed based upon your thumb. So I would like to note that you can change the angle, the relative angle between the two vectors without changing the direction of without changing the orientation of the cross product, as long as you don't get all the way to the point where you basically have to flip it around. So you still need to have that directionality going on. So a few properties of cross products. Again, they're not commutative. P cross Q is not the same thing as Q cross P. And again, that would be basic because that'd be curling from this direction versus curling in this direction. They are distributive, so you can cross P with two separate vectors added together, and that's the same thing as crossing P with one vector and then adding that to P crossed to the second vector. And they're not associative. So basically, you kind of can't combine crossing stuff together like this. Say, for example, if you have, let's say that Q and S here are both unit vectors in the x direction, then essentially Q cross S, because they're parallel, that would be 0. So it'd be P cross 0, this whole thing 0. Whereas P cross Q is say P was a unit vector in the y direction. P cross Q, that, you know, that'll if our y-axis is in this direction, if our x-axis is in this direction, then our vector would be in this direction. So based upon a typical typical right-hand rule orientation of the of your graphs, that'll give you a result that is a y cross a y cross x or a j cross I, depending how you kind of want to look at it, is going to give you a vector that is oriented in the negative z direction. Negative z crossed, and then if we, and again, if s still remains a unit vector in the I direction, negative z crossed with I is going to give you, actually I've got that on the next one, so a k cross, if I cross k is negative j, then a k cross I is j, but a negative k cross I is going to be j. So you kind of gotta keep in mind that when you flip the sign on any of these terms, the result flips its sign as well, and when you flip the order of any of these terms, the sign flips as well. So we can take the various vectors that we're trying to take the cross products of, and we can break them up into their rectangular components. And then from there, we can essentially do our cross product in order to get the resultant that is also in its rectangular components. So essentially, we can do that by taking the determinant of this little matrix here. So essentially, if you arrange your I, j, and k components of the two vectors that you're taking the cross products of, like this, and again keeping in mind that the order matters here, so this one is going to be P cross Q, and so we put the P in the second row there. And essentially what we can do is we can figure out the I components of that by going from I and slanting forward like this, and that'll give the positive components of our I vector. And that'll be P, Y, Q, Z. And then we can also angle downwards, backwards. So going like this and then kind of hitting the side and going like this. That gives us minus pz qy, and that's our I component. And then we can do something similar. We can do something similar for our j components. So j, pz, hit the edge, go like this. That's pz, qx, minus px, hit the edge, go back, px, qz, j. And then same deal for k, forward, hit the edge, go to the other side. Let's make that one blue. Plus px qy minus py. Sorry, that one looks a bit more like an R. Py qx k, which is, not too surprisingly, just what we worked out here. There's also another methodology that takes a bit more space up on the page, but kind of avoids you having to hit the edge and going back. You can just go I, j, k, and then repeat the I and j rows, columns here. And then that just allows you to not have to repeat yourself. So you can just go, you can start with your I, py, qz, minus I, pz, qy. And then your j, you get j, pz, qx, and then minus j, px, qz. And then moving on to our k, get k, px, qy, minus k, py, qx, which again just works out to the same thing as we saw above once we kind of write it all down. So that kind of helps you avoid having to keep in track kind of how you shift when you get to the sides here. So obviously, when you're doing actual cross products, actual two actual vectors, you would put in the actual x, y, and z components of those vectors in this, and then actually multiply them. So why are we worried about doing cross products? Well, cross products are what we use to basically calculate the tendency of a force applied to an object to cause that object to rotate about a specific point. So, fine example here is a wrench. If we have a wrench here that has, we've got a nut, so we put the wrench on and we basically push on the wrench from the far end parallel to the wrench. It's not going to turn. We're just going to push, and then this wrench this nut here isn't going to want to move because it's attached to something, so it'll push back, and you're not going to get any movement. Whereas if instead we apply a force at the other end of the wrench that is perpendicular to the vector from the point of origin to where the force is applied, then we get what we call a moment. And that moment describes the tendency for this wrench to want to rotate about this point. So yeah, they are defined by moments. Forces are defined by magnitude and direction, but the effect that they have upon them depends also upon where you apply those forces. So mathematically speaking, the moment of that force about a particular object is defined by this moment here, which is the cross product of the vector from the point that we're measuring it about to the point of application, crossed with the vector of the force itself. Now that results in a moment vector. That vector has directionality itself. That directionality is perpendicular to the plane, which contains both the origin here and the vector of the force that's being applied. So the magnitude of that is just the magnitude of this distance here from origin to the point of application times the magnitude of the force times sine of the angle between the force being applied and the vector. So again, if those two things are parallel, like we saw with this top thing here, then sine of theta is equal to 0, so there's no moment. There's going to be no tendency for this wrench here to want to rotate. Whereas in this instance, we got a 90-degree angle here, so the sine of the 90-degree angle is 1, so that is going to be at its maximum. So the magnitude of that moment is basically a measurement of how much that force that's being applied is going to cause the body to want to rotate about the point we're measuring it. The sense, again, is based upon the right-hand rule. So we're basically we're taking the cross product of the vector from the point of origin to the force that's applied, and then the force that's applied is the second one. So basically, based upon the right-hand rule, are the directionality of the distance, the directionality of the displacement from the origin to where the force is applied is going kind of along your fingers. The directionality of the force that's being applied is coming out of your palm, and then the vector is the orientation of your thumb. So this point here is key. That any force that has the same magnitude and direction as another force is going to have this, its equivalent if it has the same line of action, and therefore it also has the same moment. So basically, when we go back to our wrench example, if we push on the wrench from one side, it's going to generate a certain amount of moment that's going to cause this thing to want to rotate. In this example, it's going to want to rotate clockwise. If we say attach a rope to this end of the wrench and tug up on it at the same angle, in the same line of action and with the same amount of force, this moment here that's generated is going to be the same as the moment that's generated in the scenario on the top. Those are equivalent moments, equivalent forces. So we also need to define our sign conventions here. So basically, say we're looking at some object and it's subjected to forces in the plane of the structure. We'll assume it's like a flat sheet of some sort. It's got breadth and length, no depth. We apply this force here, and we want to measure how it's going to cause rotate, what sort of moment it's going to have about O. So we know that moment that's generated is going to be perpendicular to the plane. Here I'm going to just sketch quickly let's just quickly sketch kind of an axis. So let's assume this is X, this is Y, and we're going to have Z going off in this direction. So essentially, we're still kind of keeping with the right-hand rule. So again, if you, yeah, I can't really show it on the on the screen very well, but if you kind of curl your fingers from X towards Y, your thumb will be sticking out in the positive Z direction. So that is going to be basically the definition of a positive moment. So essentially, kind of when you're looking at it in the XY plane, if it's a positive Z moment, then it's going to be causing rotation counterclockwise. Whereas if it is a negative Z moment, then it's going to be causing rotation that is clockwise. So the next thing we're going to want to be looking at doing is basically breaking up our moments into rectangular components, because then we can add, subtract them easier if you have multiple moments that you need to kind of resolve into a single resultant. So again, we're still defining the moment as the cross product of this vector from the origin to a point crossed with the force that's applied to it. We can break that R term up into its various components, and we can break the force term up into its various components. And then essentially we just kind of we do what we just discussed earlier about how to do the cross product of vectors in general. Now we're just kind of breaking it up into I, Y, and FZ into individual X, Y, and Z components of the displacement vector and of the force vector. So essentially, yeah, we're just doing what we talked about here, but instead of general vectors that we're talking about, we're actually talking specific displacement vectors and force vectors in order to get our moments. So what do those things represent? Well, the individual components of your moment will describe the tendency for that moment to cause rotation about these axes. So the mx, so whatever portion ends up with your I here, that describes the tendency for this force that's applied to cause rotation about the x-axis, and so on and so forth. Now, let's assume that we're not necessarily measuring from the origin itself, but instead we have a force that is acting at a point, and we want to figure out what sort of moment it would cause, what sort of tendency it would cause for the object to rotate about a different point. Well, then we're essentially we just need to figure out what the vector is from the point that we're taking the moment about to the point where the force is applied. So we just we take that displacement vector and we break it up into its individual I, J, and K components. And then once you have that, then you just, as usual, take the cross product of these two vectors and combine them. And thankfully, we're not always going to be worried about I, J, and K, so on and so forth. At least for all terms. Sometimes you're only gonna, if you're simplifying things to a 3D structure, then you're only going to have forces that are acting, say, in the X direction or in the Y direction, and the rotation is only going to be about the Z-axis. The Z-axis isn't shown for this 2D structure, but that structure, it needs to rotate. It needs to rotate on the page. So we describe that rotation on the page as rotation about the Z-axis. So that simplifies the calculations somewhat. So we either get that if we're talking about taking the moment about the origin, or we get this this value here if we're taking the moment about a separate point B. And what we've done here is basically we've done these calculations, except we know that any of the displacements and any of the forces in the Z direction is 0, so those terms end up being nothing, which simplifies our terms somewhat.